guys, my name is Esmeralda Guerrero and this is my Anatomy and Physiology 202 modeling project. I will be focusing on the effects of epinephrine and norepinephrine on the heart. So what does this mean? Epinephrine and non-epinephrine? Well, it's actually commonly known as adrenaline and non-adrenaline. This hormone is released by your adrenal medulla that tells you either to stay and fight or run and hide. In order to better understand how these hormones work and the effect that they have on the heart, we have to understand what's going on a cellular level. Here, you see a little epinephrine molecule. They're very specific, so they have to bind to very specific receptors. Well, why don't they just cross this membrane right here? Well, these little guys are actually hydrophobic, meaning that they do not like water. Epinephrine is a water-soluble molecule, so he can't cross through there because these guys are not going to let him come through. So he has to attach himself to a beta-1 adrenergic receptor that acts as a secondary messenger in order to let it through. It's like saying you have to get a message to one of your friends that lives in the dorms, but you are too lazy to get out of your dorm and go to their dorm, so you send somebody else to do it for you. Once this binding takes place, it actually activates or turns on the heterometric G protein, which has three subunits known as beta, as represented by the little b, alpha, as represented by the A, and gamma, represented by the Y. Once this subunit breaks off, it carries with it guanosine diphosphate. This little guy is eventually replaced by GTP, or guanosine triphosphate. This guy then meets up with adenylyl cyclase in order to make magical things happen. Well, what's so magical or what's so important about adenylyl cyclase? Well, it actually speeds up the production of cyclic AMP. How this is done is through energy, or also known as ATP, adenosine triphosphate. Well, what's so important about cyclic AMP? Well, this protein kinase A is regulated by cyclic AMP. If you don't have cyclic AMP, you can't activate this guy, protein kinase A. Well, why do you need the activation of protein kinase A? I will tell you why. Protein kinase A then runs over to type T calcium ion channels, allowing for all of these calcium molecules that couldn't get through the membrane to come rushing through the cell through that channel. And so basically it goes message, 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 and then you get this whole shebang of calcium inside the cell. This activation also allows for the phosphorylation of myosin. That means that one phosphate is added to the head of myosin, which has a trickle effect and in turn speeds up actin and myosin binding, which in turn increases muscle contraction. And since your heart is one strong muscle that pumps blood to the rest of your body, this is very important. Now that we've seen things at a cellular level, let's take a look at the heart from the inside. So up in the right atrium, we have the sinoatrial node, which is also known as the pacemaker cell. This guy sets the pace. He sends out an electrical impulse down to the atrioventricular node, which then continues that electrical impulse down through the bundle of His and out to the left and right bundle branches and Purkinje fibers, these little guys, which then tells the heart to contract and push out all the blood that is in the ventricles to the rest of the body. It's quite amazing. I'll get it close so you have a better look. So it goes SN node, or sinoatrial node, down to the AV node, atrioventricular node, down through the bundle of His, and down to the left and right bundle branches of the heart. To get a better picture of what's going on, let's compare a normal heart rate to one that's being stimulated by epinephrine and norepinephrine. Both heart rates still have sodium coming in to depolarize and potassium coming in to repolarize. However, their hyperpolarization period is very different. In the normal heart rate, it is very long, or it has a longer hyperpolarization period. And in the one being affected by epinephrine and non-epinephrine, it is much shorter, allowing for faster depolarization and repolarization, which in turn allow it to reoccur over and over and over again. This is done through the funny ion channels on the pacemaker cell membrane, which in turn allows sodium to leak in to the cell and cause the spontaneous depolarization. However, you do not want to be amped up like this forever. So the body does something quite wonderful and makes an enzyme called phosphodiesterase, which stops or lowers the production of cyclic AMP, which also in turn reduces your heart rate. So you can come back to this and reach homeostasis. And there you have it. There are the effects of epinephrine and non-epinephrine on the heart.